All right, today we're putting on our detective hats and diving deep into the Linux kernel. We're going to solve one of the most common, most frustrating mysteries out there: why your computer sometimes slows to an absolute crawl, even when it looks like it's not doing anything at all. This is the core of the mystery, isn't it? Why is my computer so slow when the CPU monitor says it's basically on vacation? I mean, we've all been there, right? You're just staring at the screen, waiting for something to happen, while all the stats are telling you, hey, everything's fine. Well, it's not fine, and we're about to figure out exactly why. Okay, so here's our evidence. This is our case file. Imagine you run a command like top. You see two things that just don't make sense together. On one hand, CPU usage is way down, practically zero. But on the other, the load average is spiking like crazy. This right here, this is our paradox. This is the scene of the crime. The numbers are telling us two completely different stories. So to crack this case, we have to start by following the clues. And the very first, most important clue is figuring out what that load average number is actually telling us. Now here is the first big misunderstanding we need to get out of the way. A lot of people think load average is just another name for CPU usage. It's not even close. It's much better to think of it as the length of a line, or a queue. It doesn't just measure the tasks that are currently running. It also counts all the other tasks that are standing in line waiting for their turn. So let's get precise. The load average is counting tasks that are on the CPU and tasks that are waiting for the CPU. But, and this is the real kicker, the absolute key to this whole thing, it also includes tasks in something called an uninterruptible sleep state. Now, that's usually a process waiting on I/O, input-output, like a slow hard drive. Remember that term. It's going to be very important. Okay, on to our next clue. To really get where these processes get stuck, we need to investigate the scene of the crime itself. And that means understanding this fundamental split in how your computer works, the division between user mode and kernel mode. I love this analogy. Think of your computer like a restaurant. User mode is the dining room. It's where all your applications live, your browser, Spotify, everything. They can look at a menu and place an order, but they are absolutely forbidden from going into the kitchen. Kernel mode, that is the kitchen. It has total access to everything: the CPU, the memory, the hard drives. It's incredibly powerful, and for that exact reason, it's a heavily protected, restricted area. So why have this separation? I mean, why bother? Well, just imagine if any app, like your web browser, could just waltz into the kitchen and start messing with the stove. A single tiny bug in some JavaScript could crash your entire system. The kernel acts as that bouncer at the kitchen door, making sure that kind of chaos can't happen. So if the app in the dining room can't go to the kitchen, how does it get food? It gives its order to a waiter. In the world of Linux, that waiter is called a system call. The application packages up its request, I need to read this file, and hands it off. The CPU then does this little context switch into kernel mode. The kernel safely performs the action, gets the data, and then switches right back to user mode to deliver the results. It's a very formal, very safe, and very deliberate process. And that's the bottom line. System calls are that official border crossing. They are the only legitimate way for a regular, everyday application to ask the super powerful kernel to do some heavy lifting for it. But all this safety and control, well, it doesn't come for free. And that price tag brings us to our next piece of evidence, the hidden tax of multitasking. It's a concept called context switching. You see, every single time the kernel switches from running your browser to, say, your music player, even just for a fraction of a second, it has to do a whole bunch of work. It has to pause the first task and meticulously save everything about its current state, what it was doing, where its memory is, all of its notes. Then it has to load up all of that same stuff for the next task. All of that saving and loading is overhead. It's time the CPU is just doing bookkeeping, not actually running your code. That's what you've got to realize. The seamless multitasking we all just expect is really a brilliant illusion. It's just the kernel switching between jobs so incredibly fast that it looks like they're all happening at once. But every single one of those switches, every single time, has a small performance cost. And those little costs, they add up. And it turns out not all switches are created equal. A voluntary switch is when a program politely says, hey, I'm just waiting for the network, someone else can go ahead. That's a huge clue that points to I/O being a problem. But an involuntary switch, that's the kernel stepping in and yanking a process off the CPU because its time slices up. That points to the CPU itself being the bottleneck. Knowing which is huge for debugging performance. Okay, detective, let's review. We know load average includes waiting tasks. We know the kernel is a gatekeeper. And we know switching between tasks has a cost. We have all the clues. Now it's time to bring it all together and unmask our culprit, the infamous D state. So let's just lay out the logic. It's actually really simple, but so powerful. If our load average is high, meaning the line is really long, but our CPU usage is low, meaning the cashier is just standing there, what does that tell you? It can only mean one thing. The processes in line aren't waiting for the CPU. They have to be waiting for something else. And that something else is almost always I/O. This is the uninterruptible sleep state, or the D state. A process gets put into this state when it's deep inside the kernel, waiting for something that might be slow, like reading from a disk or getting a response from a network. And the key word here is uninterruptible. Once it's in this state, it can't be disturbed. You know, this explains one of the most classic and annoying Linux behaviors. Have you ever had a zombie process that just would not die, even when you hit it with the ultimate hammer, kill -9? This is why. If that process is in the D state, the kernel will actually prioritize the integrity of that I/O operation over your command to kill it. It's a safety feature to stop you from corrupting data. So, there it is, the solution to our mystery. Your system feels slow because a bunch of your programs are stuck in a traffic jam. But they're not waiting for the CPU, they're waiting for slow hardware. They're all trapped in that D state, waiting on the disk or the network. All of those waiting processes drive the load average through the roof, but because they're not actually doing anything, just waiting, they use absolutely zero CPU. Case closed. So the big takeaway from all this is that system performance is so much more than just raw CPU speed. It's this really complex dance between the overhead of system calls, the tiny tax of every context switch, and, as we discovered today, the massive impact of just waiting around for blocking I/O. Let's wrap this up with one powerful summary that you now understand completely. Linux executes processes by time-slicing the CPU, it transitions between user and kernel mode using system calls, and it schedules tasks fairly. But its real-world performance is dominated by syscall overhead, context switching, and blocking I/O. Now you know what's really happening under the hood the next time your idle computer starts to feel slow.